Hello students, welcome to another video for engineering statics. Today we're going to go over sections 2.4, 2.5, and 2.6. In these sections we're going to learn about the addition of coplanar force vectors. We're going to learn Cartesian vector notation and how to add Cartesian force vectors together. So let's go ahead and start here with the addition of a system of coplanar forces. In the previous video, we went over the basic geometry and trigonometry associated with a regular triangle, where you have a triangle that has each length A, B, and C have a certain magnitude, and they all have different angles. So angle A, B, and C. Now, these interior angles, when added up together, are 180 degrees, and with this geometry, there are certain laws that apply. The law of cosines, which describes the relationship between the magnitudes and one of the interior angles, and then the law of sines, which describes the relationship between each magnitude and its the associated angles. In these two laws and this basic configuration is going to be quite useful when we're trying to determine the addition of force vectors or the subtraction of force vectors and things of that nature. Now, something else to consider is, what if we are given a triangle, but one of those angles is prescribed? So say we're given a right triangle where one of the interior angles is 90 degrees. So we say we have this. So we have magnitudes A, B, and C. We have an angle of 90 degrees, which would have been angle C. So angle C is equal to 90 degrees, and then we have interior angles A and B. The law of cosines with a right angle turns into Pythagorean theorem. Pythagorean's theorem. And this is done through, if we look at the law of cosines, we see that it is minus 2ab cosine of C. Well, cosine of C, if C is equal to 90 degrees, becomes 0. So the law of cosines turns into Pythagorean's theorem, which just describes the relationship between the magnitudes of the various sides. So C is equal to the square root of a squared plus b squared. Now, again, we can also, considering that C is equal to 9 degrees, update the law of sines. When we look at it, we see that the sine of C is equal to the sine of 90 degrees, which is equal to 1. So our law of sines changes, and it shows a relationship of A over sine of A is equal to B over sine of B, which is equal to C. And that's a relationship that we can use in order to solve problems. Now that we've identified this, let's go ahead and look at how do we deal with force vectors and scalar notation. So scalar notation describes the magnitude on a given axis. So if we were to take some force vector f at some angle and decompose it, we can decompose it into force with a force magnitude for fx and a force magnitude fy. So fx is equal to the magnitude of the force vector times cosine of theta, and fy is equal to the magnitude of the force vector times the sine of theta, where theta is the angle relative to the x-axis. Now, we're not always going to be given the angle of the force vector. Sometimes we'll be given the proportional lengths of the force vector. So it's a method to describe the force vector in terms of the relationship between lengths of a triangle. So if we were given so this here is an example of a force vector that we would be given, where there's a force vector f, and the orientation of it is given through these values A, B, and C, where those are the lengths of the sides of the triangle. We can decompose this force vector f into magnitudes fx and fy, by using a proportional lengths method, where the magnitude fx divided by the force vector's magnitude is equal to a over c, where a is along the same direction as fx. So you have fx and you have a, the second equation, fy over f, is equal to b over c, where b is in the same direction as fy. And this is basically scalar notation, where we're using the magnitudes in order to describe the direction of the vector. We would need to use arrows. So we would describe this as a positive, and this is a positive. So in order to describe the sense of direction of these magnitudes, we can put arrows to describe their sense. So here, fx would be in this direction, fy would be in this direction. And this allows us to describe what is the sense of direction for these magnitudes, for this scalar quantity that we have. And it's something that you should do in terms of actually drawing the sense to help you to solve problems more effectively. Now let's look at Cartesian vector notation. Now Cartesian vector notation is different from scalar notation because it describes both the magnitude as well as the direction of a force vector. So for instance, say we're given some force vector f that's in an xy coordinate system, and we decompose it into fx and fy into components. Well, the magnitude of those components is going to be fx and fy, and the direction of these components is described using Cartesian unit vectors, where the direction is described as I with a little arrow over the top, and j with a little arrow over the top. And so in this case, if we look at x, in the Cartesian vector notation could be positive or negative. So in this case, we see that the x, we're assuming that it's a positive I because it's going in the x direction, in the positive x direction, and we're assuming it's plus j because it's going in the positive y direction. So actually writing it in Cartesian notation is the next step. So we have our force vector, and it's equal to the magnitude fx times the direction I, where I is a positive direction, so we just put the I with a tilde over it, plus the magnitude fy times the direction j, where since j is positive, it remains positive. So we have our vector, and we decompose it into the components in the I direction and plus the components in the j direction. And this is called Cartesian vector notation. So let's look at coplanar resultant forces. So say we're given some force vector F1. F1 is similar to the previous example that we did. The Cartesian vector form would be vector F1 is equal to F1x in the I direction plus F1y in the j direction. Say we're given a vector F2, and we see that this vector F2 has an I component that's it has a negative I component. If we look at it, we see if we were to decompose it, it would be in a positive j direction and a negative I direction. So then the Cartesian vector form for F2 would be vector F2 is equal to negative F2x in the I direction plus F2y in the j direction, where the negative sign from our Cartesian unit vector is applied within the Cartesian vector form. Now let's look at another example, force vector F3. If we were to decompose this, we can see that it would have a positive I component and would have a negative j component. So we look at it, and the Cartesian form is vector F3 is equal to magnitude F3x times direction times I minus F3y of J, where the negative unit vector is represented by the negative sign in front of the F3yj. And notice that in terms of this Cartesian vector form, we are actually multiplying these values times each other. And that's why we're able to move the negative I to the front of this component, as well as moving the negative I here instead of having it in front of the J. So what happens when we have various vectors, or a system of force vectors, and we want to find the resultant? Well, that's where the Cartesian vector notation really comes in handy. So we know that the force resultant is going to be equal to the sum of force vectors 1, 2, and 3. And what we can do is we can take each of those magnitudes, each component of these vectors, and add them together. So f1x minus f2x plus f3x times direction j plus f1y plus f2y minus f3y times direction j. And we've created a Cartesian solution to the force vector. And notice that if we take everything in brackets, that is described as the component of the force resultant in the x direction. Same thing with these guys summed together is the component of the force resultant in the y direction. And of course, if we were to describe the resultant force, the components of the resultant force in scalar notation, then we could simply write frx is equal to the sum, fry is equal to the sum. And note that again, in order to apply the sense, so what is the sense of frx or fry, we can use arrows to describe the direction and apply a sense to the scalar quantities. Okay. So now I'll show some kind of just a summation or a summary of some of the things we learned. We know that if we're given some force vector r, we can describe it as, or if we're trying to find the resultant force of a system of forces, and we want to find that force resultant r, we can describe it as a component, or the resultant component in the x direction and the resultant component in the y direction, where the resultant component x is the sum of all the components of force of the system of forces, and fry is equal to the sum of all the components of forces in the y direction. We can apply this Pythagorean theorem in order to find the true magnitude of the force resultant, which is the force resultant magnitude is equal to the square root of force resultant x squared plus force resultant y squared, the components of x and y. And then if we want to find the orientation of the resultant force relative to the x-axis, we can use a little bit of trig, and we'll find that the angle theta is equal to the tan inverse of the force resultant y component divided by force resultant x component. And these are just some useful equations that you'll see that you'll need to use from time to time to solve problems of force vectors. So now let's go ahead and look at the next section in the book. This is section 2.5, Cartesian vectors. The solution of 3D problems is greatly simplified by representing vectors in the Cartesian vector form, as we just demonstrated. Now, the most important thing is to establish a consistent coordinate system that you can use in order to solve problems in Cartesian vector form. In this book and in this class, we're using the right-hand coordinate system. We will use a right-hand coordinate system in this text. And if you look at the drawing, you can see my hand, and it's creating this certain shape that it's creating, where we find the thumb. I have my thumb pointed upwards, And you see my fingers curled, pointed outwards, and my wrists extended. Well, the thumb represents the positive z direction, my fingers represent the positive x, and my wrist represents the positive y. And this is called the right hand rule, where you use your right hand to establish consistent coordinate systems in terms of what is the positive directions and what directions correlate to which direction. So by taking your hand and creating that right hand, taking your right hand, creating that coordinate with your hand, you can then create a figure which describes a consistent coordinate, where you have positive x, your positive y, and your positive z. So this is a very important rule. It's something that you'll hear in other classes. It's something that every engineer should know. So make sure that you practice a couple of times, setting your hands and remembering or memorizing, what part of your hand correlates to the different parts or the different directions in the coordinate system. Okay, so let's think about, in the past we've been looking at 2D, let's think about a 3D vector, right? So say we use the right hand rule and we create our coordinate system x, y, and z. Well, the x has a unit vector of I, so a positive I. Y has a unit vector of positive j, and z has a unit vector of positive k. And they're directed along those positive directions we established with the right hand rule. Now, assume we have some vector a, which is in 3D space, just some vector. Well, that vector in Cartesian vector form would be vector a is equal to ax times I plus ay times j plus az times k. And that is how we can create a 3D Cartesian vector, right? So how do we find the magnitude of a 3D Cartesian vector? So again, we have this vector A. It has components x, y, and z. What we can do is we can use an extension of the Pythagorean theorem. Because these axes are all at right angles to each other, we use an extension of the Pythagorean theorem, and we find that the magnitude of vector A is equal to the square root of ax squared plus ay squared plus az squared. Now we can also find the magnitude of pieces or components of the A vector. So what we can do is say we have ax and ay. Well, if we do Pythagorean for a1 and ay, we'll find a prime, where a prime is a projection in the xy plane of a. And in order to get a from a prime, we can do a is equal to the square root of a prime squared plus az, where az is the only missing component. So this here is az. So we're completing that triangle to find a prime. To find the magnitude of a. Okay. Now, how do we find the directions of a Cartesian vector? So say we're given some Cartesian vector, it's in 3D space. What are the directions? How do we determine what the directions of a Cartesian vector are? What we can do is we can say we have, again, our right-hand rule coordinate system x, y, z. We have some vector A that's in 3D space. Well, we can pull certain angles. We can describe an angle alpha, which relates the A vector to the x-axis, an angle beta, which relates to the y-axis, and an angle gamma, which relates to the z-axis, right? And we can find the information or the value of these by using the cosine, a certain cosine relationship, where cosine alpha is equal to ax over a. So the magnitude of the x components of A divided by the total magnitude of A. Cosine beta is equal to AY over A, and cosine gamma is equal to AZ over A, where the right-hand side or portion of these guys can be called the ratio of magnitudes. That's what we can describe that as, a ratio of magnitudes. Now, what if we wanted to just describe the direction of a Cartesian vector, just the direction of it, but not the magnitude? Well, we can do that by using a unit vector. We can describe the direction by itself as a unit vector. That unit vector, in this case, we'll say unit vector, or UA, which is in the direction of A. So it's the directional information, but not the magnitude. Well, unit vector UA is equal to AX over A times I plus AY over A times J plus AZ over A times K, where, again, we see these ratios, right? These magnitude ratios between the component AX over the magnitude, the total magnitude A, component AY and component AZ, and so on. Now, again, as we saw above, the magnitude A is going to be equal to the square root of AX squared plus AY squared plus AZ squared. So we're using the Pythagorean theorem to get the total magnitude, and the ratio of the magnitudes describes the direction of the unit vector. So if we were to take the direction cosines relationship, and we were to take the unit vector and make them and replace like terms, then what we'll find is that we can rewrite the unit vector and describe it as equal to the cosine and the cosine direction. So cosine alpha times I plus cosine beta times J plus cosine gamma times K. And these are, these three equations are very useful equations, and you will see them again. So just make sure that you understand what a unit vector is. The unit vector just describes a direction. There's no magnitude. And also, how do you find the magnitudes? Using the Pythagorean theorem and decomposing the components or recomposing the components to get either the components or the total force magnitude. So there's some additional equations that, there's one additional equation which is quite useful, which is the direction cosines identity. It describes how these angles correlate to each other. And what you'll find is that cosine of alpha squared plus cosine beta squared plus cosine of gamma squared is equal to 1. And this relationship can be quite useful, particularly when you know two of the angles, but the third angle is difficult to find, or there's not enough information. Then you can solve for the unknown. So finally, we can take this vector A that we have, and we can describe it in a number of ways. So vector A can be described as the magnitude of A times the unit vector. So it's the magnitude times the direction, right? To give you the information. If we were to take that unit vector and further break it down, we'll find that it's equal to the magnitude of A times cosine alpha times cosine alpha times I plus A times cosine beta times J plus A times cosine gamma times K. Now, if we were to look closely at just A cosine alpha, we find that the A cosine alpha is equal to the component AX. So we can further simplify it to AX of I plus AYJ plus AZK. And these permutations, or various ways that you can create or describe your Cartesian vector, are very useful. So finally, the last section we're going to go over, and I'll let you guys go, is 2.6, which is the addition of Cartesian vectors. If expressed in Cartesian vector form, the addition or subtraction of vectors is very straightforward. So say we have a vector A and a vector B, and they each have components. Well, in order to add vectors A and B, we collect the like components together, and we can come up with a resultant force vector very easily. So in general, the generalized addition of force vectors, the force resultant is going to be equal to the sum of the force vectors. The sum of the force vectors in Cartesian form are equal to the sum of the components in the x direction, the sum of the components in the y, and the sum of the components in the z, broken down into Cartesian form, where I, j, and k describe the directions of those components, and the sums are the magnitudes. So that completes today's lesson. What you should do after watching this video is to read chapter 2.4 to 2.6. Make sure that you read it thoroughly, work out a couple of examples, and then be prepared to work problems in class, the next class. Okay, I'm Dr. Stewart, and thanks for watching the video.